So hello and welcome. My name is Wesley Walker, and today I'll be speaking to you about Bacteriopheophorbide nanoemulsions as photodynamic therapy agents. To begin, I'd like to discuss what I consider to be the three pillars of photodynamic therapy. The first is the drug, more specifically a photosensitizer. This is usually administered intravenously and then allowed to circulate systemically until it accumulates in tissues of interest, such as a tumor. At this point, light is delivered to the same tissue of interest, typically by using a laser coupled to a fiber optic cable. And when the laser light interacts with the photosensitizer in the presence of molecular oxygen, we get effective photodynamic therapy via the creation of reactive oxygen species, which just kill nearby cells. Now, of these, I'm really focused on the photosensitizer development aspect. So I think it's important to ask ourselves, what makes an ideal photosensitizer? The first property that we look for is a near-infrared excitation wavelength. This has to do with the fact that if you were to look at your hands, you would find that your skin, in fact, is not transparent. And in reality, human tissues are very heavily absorbing and scattering in the visible spectrum, except for this window from about 700 to 900 nanometers where tissue absorption is minimized. And this is what's known as the tissue optical window. So the idea is that by selecting a photosensitizer, which has an excitation peak within this tissue optical window, we will maximize the light penetration depth, which will help to improve treatment outcomes. Now, when we consider three of the most heavily investigated photosensitizers, these are the porphyrins, the chlorines, and the bacteriochlorins, we can see that structurally they look very similar. However, when we consider their optical spectra, there are very significant differences. And what I would like to draw your attention to is that as we go from porphyrins to chlorines to bacteriochlorins, there's a very significant redshifting of the excitation peak, with bacteriochlorins having an excitation peak at roughly 750 nanometers, which is right within this tissue optical window. Additionally, we would like to have a high molar extinction coefficient. This should be intuitive, as the greater the molar extinction coefficient, the more likely it is that any incident photon will actually be absorbed, resulting in a photochemical reaction. To this end, we can see that bacteriochlorins have quite high molar extinction coefficients of approximately 40,000 per molar per centimeter. And finally, we would like to have what's known as the intersystem crossing quantum yield approaching unity. Without getting into the photophysics, what you need to know is that this value relates to the frequency with which an absorbed photon results in a photochemical reaction. And so if this value approaches unity, it means that nearly all absorbed photons result in some sort of photochemical reaction, which is very useful for therapy. And generally speaking, we find that bacteriochlorins have very high ISE quantum yields approaching unity. The problem with the bacteriochlorins is that they have quite limited utility in vivo. They're generally not water soluble, which leads to aggregation, which leads to rapid clearance. For example, take palladium chelated Bacteriopheophorbide, one of the most heavily investigated bacteriochlorins. And you can see from the results of this phase 1 clinical trial that after a 20-minute infusion period, nearly all of the drug has cleared in under 1 hour, indicating just how rapidly these drugs clear. This is an issue because accumulation and uptake into solid tumors typically require extended circulation times on the order of several hours to even days. So some sort of delivery vehicle is needed. And this is where nanoemulsions come in. These are typically oil and water droplets, which are roughly 150 nanometers in size, and they can be long circulating. Our lab has previously demonstrated that a chlorine-based nanoemulsion had a 3-hour half-life in mice, which may allow for accumulation in solid tumors, which would allow for classical photodynamic therapy regimes. Additionally, the oil-water interface allows for surface loading of amphiphilic molecules. And when we consider the structure of Bacteriopheophorbide, we see that it has a large non-polar body here, and then a small polar head group on the edge. So we can expect it to accumulate at the oil-water interface due to its amphiphilicity. Additionally, it's quite well known that when these dyes accumulate on the surface of nanoconstructs, they become off-on probes. What I mean is that in the intact state, there are changes to the electronic structure such that the dye molecules become quenched. What I mean by this is that any incident photons, instead of re-emitting the energy as fluorescence or singlet oxygen generation, the energy is re-emitted as non-radiative decay only, otherwise just known as heat. And so you can say that the dyes in the intact state are inactive. By contrast, once the particle has been taken up into the cell, it is very rapidly disrupted, at which point we regain the monomer properties, which are fluorescence and singlet oxygen generation. And so you can say that the dyes have become activated upon cellular uptake. Another reason that I'm a huge fan of emulsions is because they're very simple to create. All you have to do is mix your Bacteriopheophorbide and your oil and in chloroform, at which point we evaporate the chloroform using nitrogen to form a film. Then we add water and we sonicate, and now we have ourselves a nanoemulsion. And we found that using this process, we were able to form a monodispersed Bacteriopheophorbide-based nanoemulsion. The polydispersity index was quite low at roughly 0.05, and the size is reasonable at roughly 160 nanometers. And when I performed transmission electron microscopy, I confirmed the results of the dynamic light scattering measurements, which indicated that the droplets are in fact monodispersed and quite small. I then performed some in-solution measurements where I found that the fluorescence and singlet oxygen generation are both heavily quenched. In the figure on the left, you can see that the differences in the fluorescence spectrum between the intact and the disrupted particle. And what you find is that the intact fluorescence spectrum is roughly 95% decreased compared to the disrupted spectra, indicating that the droplets are roughly 95% quenched. In the figure on the right, you have the results of a singlet oxygen sensor green assay. What we do in this experiment is we measure the fluorescence of a sensor as a function of light dose, and the sensor only becomes fluorescent in the presence of singlet oxygen. So this assay is a good measurement for the singlet oxygen generation rates. And then we just compare the slopes of the fluorescence versus light dose. And again, what we see is very significant quenching between the intact and the disrupted case. And we see that the singlet oxygen generation is quenched by roughly an order of magnitude, indicating very heavy quenching. I then moved on to my cellular uptake studies in a human epithelial cancer cell line. And what we see is that when we compare the brightness between these images, there's very little difference between 5 hours and 24 hours, indicating really rapid cellular uptake. We do, however, see very significant differences in brightness as we increase the drug concentration, indicating dose-dependent cellular uptake. Following this experiment, I moved on to in vitro photodynamic therapy using the same cell line. And what I found was a very clear dose-dependent response to both the drug dose and the light dose. So what I mean by this is you can see that for any fixed drug dose, an increase in light dose always results in a decrease in cell viability, and vice versa. For any fixed light dose, you can see that an increase in drug dose always results in a decrease in cell viability, indicating that the cells are very sensitive to changes in both light and drug dose. Just a couple months ago, we finally got this agent into animals, or into mice, I should say, and we performed a pharmacokinetic analysis by comparing our nanoemulsion formulation to a micellar formulation, which is what would typically be used in the clinic. And unfortunately, we don't really see any improvement in the circulation kinetics. However, this is really not the end of the world, as nanoemulsions are very amenable to surface modifications, which can help to improve the circulation kinetics. For example, we may want to adjust the PEG lipid loading, as this can help protect it against aggregation with serum proteins. We may also want to increase the host lipid concentration to further reduce the surface tension of the droplets. And if both of these avenues fail, we may need to completely change what surfactants are being used. But again, there are really a lot of approaches that we can take to improve the circulation kinetics. At this point, I would like to thank everyone in the Zheng lab for their help, with a very special thank you to my Professor Gang Zheng, as well as Dr. Zhuan Chen and Mr. Jiechuan Bu, as well as my committee members. And just before we go, I would like to leave you all with a few key messages. The first is that Bacteriopheophorbide nanoemulsions are really rapidly taken up into cells. Once they've been taken up into cells, they're very sensitive to PDT. The only issue is that the circulation kinetics of Bacteriopheophorbide need to be further improved. However, as I mentioned, there are many ways that we can go about this. And of course, I would like to thank you, the audience, for your time, and I would be happy to answer any questions.